Let's go.
Okay. Hello, folks. This is Chris Sneeden here. I am going to give you just some brief introductory remarks. And they're mainly that I'm old enough now that I've seen the growing field of chemical evolution. I've seen the old spectrographs. I've seen photographic spectroscopy. I've seen single slab analyses. I've seen the giants like Wallerstein. I've seen the advent of model atmospheres. I've seen spectrum syntheses come of age. Every time any one of these innovations has happened, the accuracy of abundances has gotten better and better and better. Mm-hmm. Each time they happen, then there are new issues that are now revealed. It's all a good march toward where we are now. So we have done things like even improved all the basic atomic and molecular physics. We have done various things, and we have basically squeezed the observational spectra and LTE analysis just about as far as they can be squeezed. And we find that we can get really decent results on chemical evolution of the sun and stars, but we know we need to do even better to really finish the job. And so we've now gotten to the era in which we not only can hope for NLTE, can hope for 3D analysis, we now demand it. We actually need this. And one of the young leaders in this field is Anish who will speak to us today. He got his PhD in 2016 at Australian National University, working with Martin Asplund. His thesis was three-dimensional, non-local thermodynamic equilibrium radiative transfer and oxygen abundances in late-type stars. He then went on to a postdoc at MPIA and a postdoc at Uppsala, and he's now a researcher, a senior researcher at Uppsala. And if you go to his very nice little website, his opening statement is pretty accurate. I work on making accurate models of the light that emerges from stars like the sun. Perfect. He started off as concentrating on a pure analytical NLTE and 3D modeling. And now if you look at his recent papers, he's really branching out into thinking about more global questions. So he's going to tell us all today about his role in the chemical evolution of the galaxy. Anish.
Thanks a lot, Chris, for that very nice, generous introduction. And thanks to the organizers for inviting me to give this talk. And thanks to all of you in the Zoom room and presumably on YouTube as well for tuning in. I'm quite humbled. Let me just share my screen and play. So I hope you can see that. So I will talk today about my research on developing, as Chris said, these next generation models of stellar atmospheres and stellar spectra for interpreting synthetic stellar spectra, I should say, for interpreting observed stellar spectra. And I will demonstrate or try to demonstrate how these developments can change our interpretation of the light that we collect from stars, and thus for example, properties of stars themselves, but also of the galaxy and of the universe, perhaps. To begin with, I wanted to start with this. Hope you can see my mouse here. The slide is adapted from Paul's slide, who I think last year gave a talk in the same series, and I saw Paul had logged in just earlier. So hey, Paul, and thanks for this slide. I've adapted it a little bit. So you can see here the star that we want to study on the left, and it's emitting light, and we collect the light and we get the spectrum. This talk will not deal with the various complications and challenges, significant challenges in this observational step, but more with this. So we get the light, we analyze it using some models, and we infer parameters of the star, and then we interpret those results and figure out things about atoms, planets, stars, the galaxy, galaxies, the universe. But this step here, going from the observed spectrum to stellar parameters, relies critically on the models. This is illustrated here. So the light is going emitted from the deeper layers of the star. It has to travel through the atmosphere of the star, and this requires, back here, requires models of the stellar atmosphere and how the light propagates through it. So this macrophysics on the slide here, but also microphysics. So the properties of the atom, the atomic structure, basically, of the atom that produces the spectral line we look at, also how that atom interacts with the free electrons and hydrogen and things like that. So this is the challenge I want to talk about today, constructing reliable models to aid the interpretation of the observed spectra, to get reliable stellar parameters, and thus to make reliable inferences about the universe. And that's summarized here. So we want more accurate models because this could change our interpretation of stars and so on. Just briefly, an outline of the rest of this talk. So first, I'll give a background about these modeling considerations, so 3D, here, 3D and non-LTE. Then I will talk a bit about models we have developed recently, or semi-recently, for carbon and oxygen. It's illustrated here. You'll see these plots later. Then I'll talk a bit about iron. This is somewhat more recent. Last year, this paper came out. And then I will conclude with basically a little bit about the outlook for the future. Hopefully each of these 4 sections will take about 5, 10, 15 minutes. The whole talk should be over in 40 minutes or so. So let's start with the models. So most spectroscopic analyses, at least of late type stars like our sun, currently employ one-dimensional models of the stellar atmosphere, and these models are hydrostatic, and they assume radiative equilibrium, at least in the upper layers. And it's kind of illustrated in this T-tau temperature optical depth relation on the right here. And they also assume LT, local thermodynamic equilibrium. Another way to put it is that they are assuming Saha-Boltzmann statistics for the absorber populations. Let's try to illustrate this here. Basically, in LT, you really only care about the spectral line you're looking at and its line parameters. There are indirect effects, of course, of other lines that influence the model atmosphere structure, but presuming you have a fixed model atmosphere and you're doing post-processing spectrum synthesis, then this statement holds. So this talk is about relaxing these 2 assumptions and really to relax them simultaneously. As I'll stress again later. So we want to do 3D radiative hydrodynamics to generate the model atmosphere structure. And we want to relax this assumption of LT by solving for the statistical equilibrium. And this second step effectively means that we want to consider the interaction of, we want to consider how all the other lines and all the other radiative and collisional processes influence the spectral line that we're looking at. So if we look at the sun, like so, and we can zoom in on the surface, probably everyone in the audience has seen this video before, but we see, or I'm sure everyone knows, this phenomenon of solar granulation, and happens in other stars as well, but the surface of the sun appears granulated. This is evidence of convection happening underneath the optical surface. So you have these hot uprising granules and these cool intergranular lanes where the gas turns over and flows rapidly back downwards. So with 3D radiative hydrodynamic simulations, this can be modeled. Here is a model for the sun computed with this stagger code. And we can do this for other stars as well, as for a middle pole red giant star, and illustrated on the HI diagram, now taking a picture of the surface of these different models. So we have the sun here, we have like a K-type giant dwarf here, and a giant star here, or a subgiant perhaps. No, sorry, this is a giant star. These videos have been sped up by different amounts, so it's not necessarily you cannot necessarily compare them directly to each other. I'll just point that out briefly. And here are the models on keel diagrams. On the left is the so-called stagger grid, I think first described in this paper of Magic et al. So it extends from around 4,000 Kelvin to 6,500 Kelvin or so, log Gs of 5 to 1.5. So this plot is taken from a more recent paper, Rodriguez-Diaz et al. 2022. So this talk will mostly be about or use stagger grid results, but there's also the CIFIS grid, which is calculated with a different code, an independent code, the Cobalt code. And I think this was first described in Ludwig et al. 2009. This plot here comes from Bertrand Delis et al. 2022. And you can see it covers more or less the same range as the stagger grid. So we have these two different options for 3D models nowadays. Okay, but what is the effect on spectral lines? For many of us, this is what we are interested in. So first of all, I'll show this example where we have, we calculate the vertical intensity coming out of this snapshot at the center of the disk. And if we do radiative transfer along each of these, every single point here, and we zoom in, for example, in this point, the hot granule, we'll get something that looks like this spectral line. You see it has a higher flux and it's blue shifted, of course, right? Because the hot gas is coming towards us, and vice versa. If we look at a point over here in intergranular lane, you expect kind of the opposite result, that the flux is lower and the intensity is lower and the line is redshifted. The net effect of this, because we will in practice integrate over the surface of this image here, the net effect is this dark blue line that you can kind of make out. So what happens is that we find a net blue shift, convective blue shift. The line is also broadened. The line is made asymmetric because of the different filling factors and the different fluxes from the granules and the lanes. So these various effects cannot be predicted, of course, by 1D hydrostatic models. So some parameters can be introduced to take them into account, in particular microturbulence, macroturbulence. You could also correct for the convective blue shift. But the advantage of the 3D models is that these effects should be taken into account naturally. So that reduces the number of free parameters in your analysis, which is always a good thing. Secondly, we can look at the t-tau relations that we get from the 3D models and compare them to the 1D models. And it turns out the differences between the 3D and 1D models are largest in the metal pore regime. So this black shaded region with the blue dashed line is kind of reflects the 3D model. The black is the distribution. The dashed line is the mean result, essentially. And this line, the red line, is the 1D model calculated with exactly the same code, but just hydrostatic with some mixing out theory adopted for the deeper layers. And you see that the temperatures of them, or the temperature of the 1D model far exceeds the mean temperature of the 3D model in the upper layers, which is where the spectral lines form. And this can be explained by considering how the motion of the gas that flows upwards and into the convectively stable region of the atmosphere where the lines form. That gas has to expand, and this contributes extra cooling that is missing from the 1D model. So that is especially prominent in the metal pore models, as we see here. And this, of course, will have a strong effect on spectral lines, and most notably on molecular lines, because molecules tend to be very temperature sensitive. So here is, I think, spectra caused by NH with the 1D model that you see here in black. The black curve is from the 1D model, and the orange curve is from the 3D model. And here the nitrogen abundance has been fixed to be exactly the same, and the spectrum from the 3D model is significantly stronger than that from the 1D model. And if you try to match the spectra together, you find that you need to adjust the abundance in the 3D model by around 0.35 dec. So that would be the 3D to 1D abundance correction in this case. So minus 0.35 dec, the 3D abundance, because the abundance predicted from the 3D model would go down if you were analyzing a real star. Okay, so that's all I will say about the 3D models. Next, just a few comments about non-LTE. This movie from my colleague Thomas Nordlander, sorry, I've blocked the name now, shows the temperature distribution in a 3D metal core model on the top as a function in a slice, in a vertical slice of the model. So here in the bottom, the gas is very hot, and then it cools. It's much cooler in the upper part of this plot. And you can also compute the radiation temperature, and that is what he's done here. So this is showing the ratio of the radiation temperature to the gas temperature at some frequency, 220 nanometers. The point is that in the deep layers, the radiation temperature matches the gas temperature, but as you go up, higher up, it quickly exceeds that of the gas temperature, of course. Another way to show this, and this movie now has a color bar scale to compare with. So let me start this movie again. Okay, so we start at the deepest layer of the atmosphere and we move upwards. And now we're looking down, straight down onto the atmosphere. Okay, so this is an XY plot, no longer a vertical slice, but a horizontal slice. So we start moving up in the atmosphere, the radiation to gas temperature ratio is unity, until at some point it starts to rapidly exceed unity, and how the deviation from unity is somehow correlated with the granulation features, and then later the reverse granulation features. Now these hot photons will interact with the atoms and the ions and the molecules that form the spectral lines, and they will drive departures from LTE, as long as, well, it depends how efficient the collisions are relative to the radiation, the radiative rates, the radiative interactions, I should say. And this is not known. This is not necessarily known a priori. One should really do detailed statistical equilibrium calculations to figure out if the collisional rates exceed the radiative rates. So when the collisional rates are very high, you will reproduce LTE. The more typical situation is where there are comparable, or maybe the radiative rates even exceed the collisional rates, and then you will have departures from LTE that need to be taken into account. On the right here, I have a term diagram for lithium, and the 670 nanometer line here, the resonance line, is quite an important line for determining lithium abundances in stars like the sun. So I'll say a few words about this because it also illustrates a couple of the most important non-LTE effects. So if we look at lithium in the sun, it looks like this on the left here. In 1D LTE, you have the dashed line is 1D LTE and the solid line is 1D non-LTE. This is from Carlson et al. 94. I should say it's for a very high lithium abundance, but it illustrates the point which I want to make, which is this. So what's going on in the sun? I think that it's simple to understand in the terms of a two-level atom, that the line itself is losing photons every time it emits a photon, it doesn't reabsorb that photon as would be predicted at the same rate as would be predicted by LTE, but some of those photons are lost. And then the net effect of this is that the equilibrium shifts such that you develop an overpopulation of the lower level, and then the line gets stronger. And that's what you see here for the sun. If we go to a metal poor star, this is HD 140283, a metal poor subgiant, we see now that the lithium line in non-LTE, which is in blue, actually becomes weaker than the line in LTE, which is in red. So the opposite case that we saw for the sun. So what's going on here? It's a different effect. There are various effects, but these are the main effects. So in this case, we have these hot photons coming in from the deeper layers so UV photons, like I showed with the movie previously. The radiation temperature is exceeding the gas temperature, so there's an excess of these photons relative to LTE. These are absorbed by the lithium ground state, for example, and that overexcites the ground state or even over-ionizes it. So you have the opposite case to what you have for the sun. So the ground state underpopulates and the line gets weaker. So this tends to happen in the metal poor case and not for the sun, because the metals, with fewer metals, there are less other lines and so on, continue bound-free transitions as well, to block these UV photons. So that's basically why this effect becomes more prominent in the metal poor case. So I will mention these two effects in the coming slides as well, in the context of carbon and oxygen and iron. One final interesting thing to note about this plot, which is from Lind et al. 2013, is this black dotted line, which is in fact the 3D LTE profile, albeit with 0.3 dec lower abundance of lithium. And you see that when you go to 3D, it's not simply a scaling of the line profile, but the shape of the line profile is also affected by the non-LTE departures from LTE. In other words, the width underneath the black dotted line and the blue line are equal, but still the line shape is slightly affected. So just to conclude this first section, what we want to do is, calculate the non-LTE effects in full 3D. So we want to relax both of these assumptions simultaneously. These movies show the contribution function for the oxygen triplet in Procyon, and you can see that the line formation is just qualitatively different. So although 1D non-LTE is probably it's certainly much better than 1D LTE, at some point we do want to go to 3D non-LTE because this seems like the most realistic description of how spectral lines are forming in stellar atmospheres. Okay, then I will now quickly present some results for carbon and oxygen that were published in the literature 3 or 4 years ago, I think. Just as a recap, where are carbon and oxygen forming in the universe? So to start with, they are formed in massive stars in hydrostatic burning, helium burning, the helium burning stage, basically. And these carbon and oxygen are released into the cosmos when these stars explode as supernovae or collapse supernovae. We also think that carbon is produced in other processes via stellar the cosmos is enriched in carbon via stellar winds. For example, AGV stars, and also perhaps massive, rapidly rotating stars via measurelessly dependent winds. It seems it's an open question how the relative importance of these two sources of carbon are, as far as I understand. I had a look at these two papers, for example, and they seem, if I understand them correctly, they seem to be pointing at this latter side as being probably perhaps more important than AGB stars, but it is still an open question. Regardless of where this carbon is coming from, we can always collect carbon and oxygen abundances and plot them like so, and try to interpret the results. So here on the y-axis is the carbon to oxygen ratio relative to solar. So solar is 0, the dotted line here. On the x-axis, we have oxygen to hydrogen as the metallicity tracer. Again, the sign is at 0, so the sign should be corresponding to this, somewhere around here. And the symbols have been labeled with basically what galactic population the particular star may belong to. And this analysis is 3D non-LTE. It's from this paper here from 2019. And we see, to begin with, in the metal poor regime, what looks like a plateau in carbon to oxygen. This can be understood or interpreted as carbon and oxygen being formed and released into the cosmos via massive stars, helium burning. And at higher metallicities, we also see this upturn, which can be interpreted as winds, perhaps AGV stars or metallicity dependent winds from massive stars. Okay, but the point of this talk is to illustrate the impact of 3D non-LTE on results like this. So I will now talk about what this trend looks like in 1D LTE. Before that, just to summarize what the effects are on these different species. So we look, the sample corresponds to around 170, maybe 180 stars, FG dwarfs. Iron is coming from iron 2 lines in 3D LTE. Iron 2 doesn't show significant departures from non-LTE, at least in this regime. Carbon and oxygen are coming from high excitation lines. So at high metallicities, we're using the optical the pair of optical lines at around 500 nanometers. This contour plot illustrates the abundance corrections for those lines at high metallicities. And the scale, actually in the next 4 plots I'm showing you, I'll just point out that the scale is always negative. The abundance corrections are in all cases negative, and so the 3D non-LTE abundance for carbon and for oxygen is always smaller than the 1D LTE one. So for these carbon lines, we see small effects at high metallicities, but we're also using the oxygen triplet, and these have very large effects at high metallicities. As you see here, this is now approaching 0.5, minus 0.5, minus 0.6 dec. The same oxygen triplet is, we also use it at low metallicities, and the effects become rather small. So even approaching no correction at all. But at low metallicities, carbon starts to show larger effects. So we're using infrared lines, for example, this one here, 940, and now we're getting effects of the order 0.2, 0.3 dec. You may have noticed that these 4 contour plots tend to show the same behavior, in that, especially at higher TF, but also to some extent at lower log G, the abundance corrections become more severe. And this can be related to, for example, higher ionizing flux in these higher TF models. Low log G could be related to collisions, the collisional efficiency, and which would bring the solution back to the LTE one. In any case, let's look at the results. So this is again the 3D non-LTE result with my sketched trend overdrawn. So with the plateau here and this upturn here. So 3D non-LTE, 1D non-LTE, the the plateau starts to go away, you start to see a bit of an upturn, and perhaps the scatter is slightly changed, but this is more dramatic in 1D LTE, where now you clearly have a trend in the metal pore case, and also the scatter here is quite severe. So the trend is largely driven by the effect on carbon, the carbon-1 lines. The scatter here is mainly driven by the effect on the oxygen lines, and really it's the non-LTE effect here. Whereas here it's both 3D and non-LTE effects affecting changing the trend. Now this is interesting because if you see a trend in one of these plots, that tends to imply some extra source of whatever element you're looking at. So I think previously this trend was observed in 1D LTE and was interpreted as perhaps a signature of POP3 stars releasing very carbon-rich ejecta into the cosmos. We find that it's this flat, we instead find this plateau here, at least down to OH of minus 2.5 or so. Perhaps, well, quite likely this, if you go to even lower metallicities, you will start to see an upturn here. But at least at this metallicity, we do not see that anymore. We can also take a closer look at these more metal-rich stars in the thin disk in particular, and some of them have confirmed exoplanets and some do not. So we can compare these two populations. And this is shown in this slide here. On the left is the 1D LTE result. So the blue points correspond to stars with planets, and the black squares are stars without planets. And the two distributions seem to follow each other quite closely. On the right is the same sample, but now analyzed in 1D non-LTE. And now you can perhaps convince yourself that the stars with planets have separated themselves more, for the most part, from the stars without planets. This is mainly a non-LTE effect rather than a 3D effect, but the 3D non-LTE result is shown here. I can flip back forth, so it's a slight difference in 3D non-LTE, but you still see it. So the result is that we find that stars with planets, for some reason, seem to have a higher C/O ratio than stars without. And, we weren't the first to find this. I mean, I've seen this before in Pavlenko et al. 2019. Perhaps there were other papers that I'm not aware of as well. The interpretation of this, I do not have really any comment on. I don't know necessarily why. I think there are many, many different ways one could start to interpret this result. But I think it's an interesting result in any case. Okay, then I will maybe spend 5 minutes or so talking about iron before going to my conclusions. So last year we had a paper out, Amarsi, Lilligren, Nissen et al. 2022. We looked at iron lines and tried to compute abundance corrections or abundance differences in 3D non-LTE versus 1D LTE. This is illustrated here on this plot. So now negative means that the 3D non-LTE result is larger than 1D LTE. So the sense is opposite to the plots I was showing previously. We did this for 100, 200 or so lines from the line list of Joffrey et al. 2014. We looked at, again, FG dwarfs, the metallicity range of -3 to 0. This plot here is showing results for FENH of 0. Each of these points corresponds to different lines and different stars. So the darker points are for the warmer dwarfs, and the lighter points are for the cooler dwarfs. The circles are Fe1 and the triangles are Fe2. They tend to follow this same pattern when plotted against reduced equivalent width. And of course, this is reflecting saturation of the lines in the 3D case versus in the 1D case. And that's what's driving this very steep, very severe abundance differences at this particular equivalent width. So if you change the microturbulence, which changes the amount of saturation, in the 1D models, you get a very different looking plot. And this is basically the idea of how microturbulence is calibrated for real stars. With 3D models, right, you kind of bypass this complication of having to calibrate microturbulence. So you could try to, what is done in practice is that microturbulence is calibrated empirically in a similar way. If you imagine that the 3D non-LTE model is the observation, you just basically try to flatten this trend. But it's not clear how perfect that calibration will be, because if you're just using a one-dimensional, a scalar microturbulence, and you're looking at lines different. If you're using that same microturbulence for different lines, different species, that may not be appropriate. So there will be some, using microturbulence will incur some uncertainty into your analysis. And even if it doesn't, it is an extra free parameter in an analysis that is often already suffering from degeneracies. I mean, yeah, if you want to also derive effective temperature, surface gravity, and so on. So this is another advantage of using 3D models. So, okay, let's ignore these rather strong lines and look at the weak lines. We find that the effects are largest for warm and metal poor stars, as has been reported earlier in various studies. And this can be interpreted in the context of these plots I've showed earlier, the steep temperature gradient in the 3D model, which is the blue dashed, or the distribution here, compared to in the 1D model, and the excess ionizing flux in metal poor stars. And these various effects will be coupled together, as I will illustrate with a couple of examples. Now, this plot here is from Rana Ezzedine et al. 2017. It's showing, for the most part, 1D non-LTE minus 1D LTE abundance corrections. So now the sense is such that positive numbers means that the 1D non-LTE abundance is larger than 1D LTE. So 1D LTE analyses of iron, or of iron 1 lines in particular, will underestimate the iron abundance. Your star will be too metal poor than if you use 1D non-LTE or 3D non-LTE. So they did an analysis for several stars, and they found this overall trend with metallicity. I was reflecting a bit on this just before the talk, and I guessed that the 3D non-LTE versus 1D LTE trend would look something similar, at least in the most metal poor case. Perhaps in this regime here, -1 to -2, or maybe even -3, there will be a change in the gradient, perhaps a steeper gradient. But then asymptotically, I would expect it maybe to follow the same, more or less the same trend. So it would be offset upwards because of the steeper gradient in this regime. Now let's look at a few of these stars more closely, and let's start with the HD 140283 again, which is a metal poor G subgiant. So here I have plotted iron abundances line by line. So each of these black points is an iron abundance inferred from a single iron line, iron 1 line, and the orange ones are the same for iron 2 lines. Now it's a function of excitation potential. So the black and the orange are 1D LTE. The gray and the blue are 3D non-LTE. That's what 3N stands for in this diagram. And you see several interesting things. I'll talk through them one by one. Firstly, there is a clear trend in the 1D LTE iron 1 abundances. You might ask, well, because trends in excitation potential, this excitation potential versus iron abundance plane are often used to calibrate effective temperatures. You may ask, what does this trend that you see, which is that you see in the 1D LTE case, but you do not see it in the 3D non-LTE case. You might ask, what does this trend correspond to in terms of effective temperature? And it turns out to be around 300 Kelvin. In other words, the 1D LTE analysis can give you an error in your derived effective temperature of the order 300 Kelvin. Now you can do something similar comparing RN1 to RN2, which is there is a large offset here that you see in the 1D LTE analysis, but not in the 3D non-LTE one. Not so much in the 3D non-LTE one. So this offset here corresponds to 0.3 dec in log G. So the RN2 lines are sensitive to the surface gravity more so than the RN1 lines. And these ionization imbalances are often used to calibrate surface gravity. So a 1D LTE analysis of the star using these lines could correspond to an error in log G of 0.3 dec. And finally, and perhaps most clearly, there is a difference in the mean iron abundance in these two analyses. So the 1D LTE is about 0.2 to 0.3 dec lower than the 3D non-LTE one. That's all I'll say about that star. Let's go to even more metal core stars. So I think this one here is the Cathal star, which is a G-type dwarf. And I'll show a couple of plots from my colleague Sis Lagay. His recently submitted paper. He analyzed the star in 3D non-LTE. So on the x-axis here is the 3D non-LTE, is the iron abundance. This one here is 3D non-LTE. This triangle here is his 1D LTE result. And the y-axis is the alpha to iron abundance ratio. And you see that it stays roughly, it doesn't change so much vertically, meaning that his alpha abundance is derived from, I think, magnesium and perhaps silicon or titanium. They have a similar effect, a 3D non-LTE effect as the iron lines that he used. But focusing on iron, he derives various numbers for the iron abundance, 1D LTE, and so on. A couple of results to focus on. So the 1D LTE to 3D non-LTE difference, the abundance correction, is 0.47 dec. One could also do a 3D LTE analysis like this, 2.7, and then try to correct it for non-LTE effects by doing the non-LTE calculations in 1D. So this would be a cheaper way of calculating the total 3D non-LTE effect without doing fully consistent 3D non-LTE calculations. And it's been employed in the past in the literature by various people. I think I myself may have used it at some point. But you find that if you work this out, because he's done all of these analysis, you get this value here, 2.95, which is still 0.3 dec lower than the consistent 3D non-LTE result. So that's the main result I want to illustrate, emphasize here, is that this 3D LTE combined with 1D non-LTE was not the same as full 3D non-LTE, especially in this extreme metal core regime where the effects become very large. So the 3D and the non-LTE effects, especially for iron, are coupled together. And the second point I will mention briefly is that, so you see that the iron abundances kind of shift to the right, but these other black points, I think, are all 1D LTE. So one could envision that maybe 3D non-LTE effects would affect these other stars similarly. And perhaps this has implications for the scatter that you see in these various abundance plots in the metal core regime. Perhaps a lot of the scatter is not intrinsic, but due to the analysis, the method of analysis. And this also has implications on the inferred properties of the population 3 star that presumably enriched the gas cloud from which the Cathal star was born. So this has analyzed the abundance pattern in 3D non-LTE. Now it's complicated because there are various other parameters involved. Some of them are are kind of really free parameters, fudge parameters even. But what seems to be the case is that using 3D non-LTE compared to 1D LTE seems to narrow the range of acceptable in terms of chi-squared fitting progenitor masses for these stars. Moreover, it tends to favor lower progenitor masses. So its best fitting mass is, I think, around 11 solar masses. So possibly, if you are doing these types of analyses where you're trying to infer properties about the population 3 stars, the first stars, it is perhaps especially important to consider 3D non-LTE effects when you are analyzing iron. Okay, I'm running a bit slow, so I will just check my slides. Okay, maybe I will skip now to the conclusions. Then, just to wrap up, I hope I've convinced you that these 3D non-LTE effects are important in analyzing the spectra of late-type stars. These effects are dependent on the line, the species, and the star. We saw various effects of different magnitudes for carbon, oxygen, and iron lines in different stars as well, tending to be more severe as you go to hotter stars and perhaps to lower surface gravities. I didn't show this, I didn't have time, but the effects can reach up to 0.8 dec for iron in the most metal poor stars that we have encountered so far. So these can be very significant, and I've also tried to illustrate how this can influence our interpretation of the stellar parameters and the abundances that we eventually derive. So my recommendation is that we should try to correct for these effects, these 3D and try to correct for the deficiencies in the 1D LTE models. Or at the very least, we should avoid problematic lines. If we know that a particular line is very sensitive to these effects, then it's better. Let's just not use that in this analysis. Now, there are data available to help with either approach. Really, I think a combination of these two approaches is probably what's called for the time being. And the data that are available can help with both directions. So very briefly about these data, we have 1D non-LTE departure coefficients presented, for example, in this paper here from 2020, calculated on a large grid of Mark's model atmospheres covering FGKM type dwarfs and giants. We've done this for 15 elements. So these departure coefficients can readily be read into many different 1D LTE spectral synthesis codes and correct the line opacity on the fly, so without incurring extra cost to the user. This plot here shows sodium abundances from Galar in 1D LTE, and then next in 1D non-LTE using this approach of departure coefficients. And you see that the scatter dramatically reduces here, and also the trends that you get for the dwarfs and the giants, they tend now to become closer together. So that was 1D non-LTE. If we ask what about 3D non-LTE, we have there are various grids of spectra and of abundance corrections available. So most of the work that I'm involved in is related to the stagger grid, which is again illustrated here from Magic et al. There are grids of spectral lines available for the BAMA, the H alpha, H beta, H gamma in this paper here from 2018. There are also spectra for the lithium resonance line. Sorry, this is a mistake here. I should say 2021, I think. And also the CIFIS, there are similar calculations on the CIFIS grid for the lithium line. There are results for carbon and oxygen for dwarfs and subgiants on the stagger grid. and also for iron-2 and 3D LTE, down to -3, Fe1H -3, the non-LTE effects are rather muted for Fe2 lines. And more recently, we have iron-1 corrections for iron-1 lines for dwarfs in the stagger grid. So I think my main conclusion is that we should take these effects into account and recommend, well, I encourage people to consider looking at these data and seeing how these data can help them at least estimate the uncertainties involved in their 1D LTE analyses. And with that, I'll happy to take any questions. Thank you for listening.
Thank you, Anish. Thank you for a great talk. Applause. So now we're going to go to questions, and you can put your question on the chat, or rather, we prefer that you ask your own question. Just raise your hand, and I will call on you. I can see already. Says Charles Cowley, but I'm sure it's not Charles.
Yes, it is.
Yes, it is. Okay.
Great talk, by the way. A lot of modern abundance work on FGK stars has been done using the differential method, and accuracies have been claimed below 0.02 dex, typically, some even below that. And I just wonder if you'd comment, have you looked at this at all in terms of the effects of non-LTE, where and when it would influence the differential abundances? Because that's a question.
So often for solar twins, this is usually where differential abundance analyses are very powerful and often used.
Yes.
So stars with very similar parameters to the sun. And so in that case, you would need very, very severe corrections, and also a very steep gradient in those corrections with stellar parameters for these effects to influence those analyses, right? And now I think I've seen it written somewhere, perhaps by Paul Erik Nissen, who I saw at some point in the Zoom room, that these effects are not so significant for differential analyses of solar twins, with the exception perhaps of lines like the oxygen triplet. And this is the huge effects at solar metallicities. So perhaps also maybe for the potassium resonance line, one could envision that this could be important. But it's true that the differential analyses of very similar stars will bypass many of these problems. Now, if you want to study metal poor stars, for example, or stars that are not like the sun, then you have all of these problems. You cannot get around these problems.
Yes, you'd have to analyze one relative to the other.
Yeah, exactly.
Thank you.
Thank you.
Okay, so I think the next one would be Simone.
Can I?
Thank you very much for your talk. My question is about the metal pool stars. So we have some large photometric surveys searching for metal pool stars, and the estimates of metallicity are based on results from spectroscopic surveys. But you show that the effect, the 3D non-LTE effect may be important for the metallicity scale. So how to reconcile this? What do you think would be the effect of this 3D non-LTE analysis on the photometric surveys?
I don't know the precision of these surveys. So that would be the main thing. If we're talking about precisions that are better than 0.1 dec or so, then this would have an effect.
No, it's I could say 0.3 or even 0.5. Sometimes not that.
then one could still correct for that empirically. I mean, I showed this plot from Ezzedine et al., which showed a very simple relation of how the correction goes with metallicity. And one could envision simply applying something like that to get a better estimate. But it would, if the precisions are of the order 0.3 dec, then unless you're looking really at the most metal poor stars, like below -3, unless you're looking at that, then it probably would not be significant to your analyses, would be my guess, but I'm not sure.
Thank you.
Thanks.
Okay, thank you. So the next one would be Oleg. Please, Oleg.
Thanks, Anish, for a nice presentation. And I hate to be this person, but still I ask this traditional question: what about magnetic fields? And of course, we shouldn't, we shouldn't approach this question from this very generic traditional perspective. I'm more interested in your assessment of the various articles that were published based on 3D magnetohydrodynamics models of solar type stars, where various differences relative to non-magnetic models were claimed. So do you think it is worthwhile to take magnetic fields into account and eventually recompute all these 3D grids, including magnetic fields?
Thanks for the question. My impression is that these are a smaller effect than the 3D effect and the non-LTE effect. We did some calculations. I was involved in some calculations as well for the sun, the oxygen triplet, which is sensitive to Zeeman splitting. And we found corrections of the order 0.01 dec or so, I think consistent with several papers that applied, for example, the local dynamo description of the magnetic fields. These papers that describe much larger effects are applying, as I understand it, strong vertical magnetic fields in their models, which are perhaps possibly not realistic of the quiet photosphere. So that's my impression. But of course, it's worth in the future revisiting this, especially in the context of the solar abundances. That would be the first place to look, I think. Well,
thank you.
Thanks.
Nicolas, please.
Yeah, if you have, in order to compute the non-LTE effects, you have to have a very good model of an atom or ion. I mean, to know all the transition probabilities. That's one for the radiative transitions. Now for the collisions, if you know all the cross sections for the collisions with the electrons and with the neutral hydrogen atom, are you safe, I mean, to compute non-LTE for any model of star?
So we have the complete description of the radiative and collisional transitions. And the question is, are we safe?
Yes.
There are also uncertainties in the model atmospheres themselves, right?
Mm-hmm.
So we have the models for the sun are most likely more reliable than models for giants, for example, metal poor giants in particular.
Mm-hmm.
So yes, the model atom is only one element contributing uncertainties in these analyses. There are other uncertainties.
And for the cross sections.
Pardon me?
So what about the cross sections?
The cross
If
section.
you know them, I mean, if you have very good values for the collisions with the electrons and the neutral hydrogen atoms, are you safe? I mean, to get to compute the nullity effects for any star.
Yes, well, as long as the model atmosphere as well is reliable.
Okay, yes, sure.
This is the
okay, that's right. Okay,
big uncertainty as well.
okay, sure. But I mean, that's yeah, okay. But the only unknown is the model atmosphere. That's it, if I understand correctly.
Mm-hmm.
Huh? Well, yeah.
Yes, I guess. Well, there will always be more effects that need to be considered.
Okay, thanks.
Thank you.
Good talk.
Thanks.
Yes. So any more questions? If
I
not,
will say, may I say, it was nice for me to see you all again. I have not seen you all since, I don't know how long, a century probably. It was last century, of course, for many of you. That was a good, pleasant surprise to see you all in good health, I hope.
it's wonderful. Yes. Let me just ask one more question, Anish, if you don't mind, concerning the differences you find in the populations of stars that you call with planets and without planets. Those are very interesting results for sea overall. Do you know which population of planets you're looking at? Are you looking at hot Jupiters, or if those stars have mostly small planets? Are they RV planets? Are they transit planets? Do you know anything about the population of planets?
They were mostly hot Jupiters, not entirely, but mostly. I forget how they were detected right now, but yes, hot Jupiters is the main.
Okay, so yeah. Okay, interesting. It would be interesting to see if they are also present when you have terrestrial planets or smaller planets, right? Okay, one last question from Charles, please, before we let you go. Thank you.
Okay, thank you. This is a comment. It's relevant to Oleg's question about magnetic fields and solar type stars or FGK stars. If I had to make one general criticism of modern abundance work, is that they use too strong lines. If you use weak lines and measure equivalent widths, then the results that you get are independent of the broadening. And lines, let's say, above 50 milliangstroms, at least in solar type stars, are quite influenced by curve of growth effects. So you have to get down to 20 or even 10 milliangstroms in solar type stars to get accurate abundances.